In this lecture, we consider the methods of estimation of parameter vector beta in the linear regression model. In the linear model y equals x beta plus epsilon, the parameter vector beta is unknown. Therefore, to use the model for prediction purposes, we have to estimate these unknown parameters. One method of estimating beta is minimizing error sum of squares subject to vector beta. Since the error term epsilon equals to y minus x beta, the error sum of squares is y minus x beta dash y minus x beta. If we set x beta as theta, the error sum of squares becomes y minus theta dash y minus theta, which is the norm y minus theta squared. To minimize the error sum of squares, first we consider this graphical method. In this case, the error sum of squares is norm y minus theta squared, and we minimize it subject to theta, which belongs to the range space of the matrix X. We use capital omega to represent the range space of X. Now, we let vector theta vary in the range space of X as shown in this figure. Note that the square length of vector y minus vector theta, that is norm y minus theta squared, is minimum for theta equals theta hat when y minus theta hat is orthogonal to the range space of matrix X. We have already noted that the square length of vector y minus vector theta is minimum for theta equals theta hat when y minus theta hat is orthogonal to the range space of the matrix X, that is omega. Hence, we can say that theta hat is the unique orthogonal projection of y on omega. Then, x dash into y minus theta hat equals to 0 vector, and that implies x dash theta hat equals to x dash y. Now, by substituting theta hat equals to x beta hat, we obtain x dash x beta hat equals to x dash y. This equation is called the normal equation. If the columns of X are linearly independent, the matrix X is of full column rank matrix. Then the rank of X is P, and hence the inverse of x dash x exists. Now we have a solution for beta hat. That is, beta hat equals to x dash x inverse x dash y. This beta hat is called the ordinary least squares estimate of beta. In the second method, first we consider the error sum of squares epsilon dash epsilon, which is equal to y minus x beta dash y minus x beta. Since beta dash x dash y is a scalar, its transpose is also a scalar. Therefore, by simplifying equation 9, now we can write the error sum of squares as y dash y minus 2 beta dash x dash y plus beta dash x beta. By differentiating this error sum of squares with respect to beta and equating to 0, we can obtain the result in equation 10. That implies x dash x beta equals to x dash y, which is called the normal equation. From the normal equation, we derive the estimated value of beta, which is beta hat, and is equal to x dash x inverse x dash y. Now, by substituting beta hat, we can find the fitted regression y hat, which is equal to x beta hat. The estimated error vector E is called the residual vector and is equal to y minus y hat, which is equal to y minus x beta hat. By substituting beta hat, we obtain this expression. We use P to denote x dash x inverse x dash matrix, which is a symmetric and idempotent matrix. Look at this equation. We can write theta hat, which is x beta hat, as Py. This means P is the linear transformation representing the orthogonal projection of n-dimensional Euclidean space En onto omega. Similarly, I minus P represents the orthogonal projection of En onto the orthogonal complement of omega. Therefore, now we can write vector y by combining these two linear transformations, that is y equals to Py plus I minus Py. This represents a unique orthogonal decomposition of y into two components, one in omega and the other in the orthogonal complement of omega. Now we prove this theorem. The first part is obvious. To show that P and I minus P are symmetric, consider their transpose matrix. We can clearly see that transpose of P is equal to P and transpose of I minus P is equal to I minus P. Therefore, both matrices are symmetric. Now, to show that they are idempotent, simplify P squared and I minus P squared. In P squared, we can note that x dash x inverse cancels out with x dash x. Then P squared is equal to P, and hence P is idempotent. By using P as an idempotent matrix, we can easily show that I minus P squared is also idempotent. In the second part of this theorem, we have to find the rank of I minus P. Since I minus P is symmetric and idempotent, rank of I minus P is equal to trace of I minus P. Since I is n by n matrix, trace of I is n. And now we have to find the trace of P. For any three matrices A, B and C, the trace of ABC is equal to trace of CAB. Then we can write trace of x, x dash x inverse x dash as x dash x inverse. Then we have the trace of an identity matrix having dimension P. Therefore, the trace of P matrix is P. Then the rank of I minus P is n minus P. In the third part, we have to show that I minus P times x is equal to 0. By substituting P as x, x dash, x inverse, x dash to this equation, we can easily show that I minus P times x is 0. This completes the proof of the theorem. The minimum value of error sum of squares is called the residual sum of squares. Hence, the residual sum of squares E dash E is equal to y minus x beta hat dash into y minus x beta hat. When simplifying this, we can see that beta hat dash is common for these two terms. Look at the expression within brackets. That is the normal equation, and hence this term is equal to 0. Therefore, the residual sum of squares is equal to y dash y minus beta hat dash x dash y. By using normal equation, if we write x dash x beta hat in place of x dash y, we can get another expression for the residual sum of squares. We have already shown that the residual term E equals to I minus P times y. Using this, we can get another expression for the residual sum of squares. Since I minus P is symmetric and idempotent, now we can write the residual sum of squares as y dash I minus P times y. Now we do this simple example. In this example, we have two independent random variables, y1 and y2, with means theta and 2 theta respectively. We will find the least squares estimate of theta and the residual sum of squares. By using the respective means, first we write the regression equations for each y variable. Then we combine these two equations and write them in the matrix form as shown here. By substituting X matrix and Y vector, now we can find the least squares estimate of theta. To find the residual sum of squares, we use this expression. After computing x dash y and y dash y, we can now find the residual sum of squares. We can find the answer for the previous example also by using first principles. From the two regression equations, we can get the error terms. Then we minimize error sum of squares with respect to theta, and then we can find the least squares estimate. By substituting theta hat to this equation, we can easily obtain the residual sum of squares.